and they start testing. What is the first problem that will arise? In this scenario, for the tester, what is the first problem you think?
Environment change.
Exactly. From a testing perspective, the first point this person would say is app is not working. It will not work. This is because the server has changed. The environment has changed, right? Here there are different computers. Here there are different computers. There could be different OS levels, different softwares, different levels of those softwares. There could be so many different dependencies, which will impact the execution of the application. So environment is changing. So that means the application has some dependencies, and because of which it doesn't work in test system. Right? So to overcome this, if you remember, I was talking about virtualization. Right? When I was talking about the VM machines and all the Dockerization and all that, I gave an introduction to virtualization. So what virtualization does is it takes the status of these servers or server, right? Probably all of these are put in one server. So I will basically templatize it. That means I'll create like a snapshot. The status of this entire server will be saved. It's like I take the entire server and then try to put that into a different machine, virtual machine. Right? It's like all the dependencies, entire this computer is put in a different computer, right? So that is templatization. But when you do this, there are certain problems. Okay. The problem is with respect to virtualization, the hardware consumption would be a lot, right? So this is the scenario, guys. Hope you have got a big picture on what exactly this is and why it is required. Right, so we are doing virtualization now. Okay, so let me erase this. So in virtualization, what happens? So let's say I have a server. I'll draw the memory here. Let's assume that I have a memory. This is RAM memory, which is, let's say, 16 GB. That's a very big server. Okay. Now, the templatization that we have done, right? That the template that we created with respect to the development environment has to come in. So we will have, let's say, first tester for this person to test the application. We will have to create a VM. I'll say VM1. Virtual machine. So that means there are some components, so some resources which are getting allocated here. We'll talk in terms of memory. So this virtual machine, let's say, is created with 6 GB. Okay. So out of the 6 GB, this is a computer now. So you're blocking 6 GB of memory out of 16 GB to this machine, which is physically not there, but virtually we are creating so that we can give access to the tester. Now let's imagine the application that is there is actually requiring, let's say, 4 GB memory. The application is requiring 4 GB. So that means 2 GB is idle. This 2 GB is not used. Then I have another tester. For this person also, I'll have to create the application. Okay. So let's say here the virtual machine 2 that we are creating, maybe I've given very small resources. So I will say 4 GB so that I have 10 GB covered. For this virtual machine, I've given 4 GB. In this 4 GB, let's say 1 GB is wasted, not used. That means 3 GB is used. with respect to the server, when you are testing, only 4 GB is 3 GB is used. Let's assume that I have another person. The remaining 6 GB memory, I'll create another virtual machine. Assume, only from theoretical perspective, assume that we are using another 6 GB memory. So total 10 plus 6, 16 GB memory is used. So let's say, again, same like this, maybe 3 GB is used, 3 GB is free. Okay. So this is free. So if you add out of 16 GB, how much of the memory is actually being used? 4 plus 3, 7, 7 plus 3, 10 GB is used. So that means the remaining 6 GB is wasted, unused. Now, if you would have used the resources appropriately, the consumption, right? The consumption would have been appropriate, then the performance of the application would also have been very good. This is the biggest problem because you are trying to split the physical server into virtual machines. They are independent computers. So they are independent machines, though virtually, but independent machines are created, and we will have locks. The resources are dedicated or locked. Now, if we use the alternative approach, which is, this is one of the solution. This is solution 1, which is virtualization, which is used to solve the problem of testing the applications. We are basically trying to ensure that there are environment dependencies are not hindering the testing process. Now, in Docker, what we do, Docker is not a physical right partitioning. It's more like a OS level containerization, right? I mean, OS level we'll try to split. So let's say I have the same server, and it is also having, I mean, same server, right? So it has 16 GB. Right. Now, Dockerization is basically an application level partitioning that we do, application level splitting, right? So we create containers. That's what Docker allows us to do. So let's say I have container 1. Okay, this is app 1, the same app, but I'm creating this as first app. Let's say I'm assigning whatever memory I wish. Okay, so let's say I'm assigning the same whatever memory is used, right? 4 GB is used. So I'll only assign 4 GB memory for this application, and all the memory will be used because there's no operating system. It's just an application. Similarly, I'll take the second app, I mean the same app, second container I'm creating, and here I'll create 3 GB. And here I'm also giving again 3 GB because that is what used here, right? So I'll only try and give that particular memory. So now you can see out of 16 GB memory, we are using how much? 10 GB memory, which is allotted. But even after giving this 10 GB, we still have 6 GB to be used. That means we can create more applications. You can create more containers. Right? So that's the logic here for your Docker system. So when you try to compare the solution 2, which is containerization using Docker, there are a lot of advantages that are brought. We have seen the comparison between Docker and virtualization, if you remember. So when we talk about a virtual machine, and both have every technique has its own advantages and disadvantages. It's not like only disadvantages are. The primary difference between the Docker and virtualization is, in virtualization, you can have your own operating system, your choice. The guest operating system that we talk about, you have your own option. Whereas in Dockers, which basically is containerization, here we will have same guest OS. For application, you'll have only one operating system. Because operating system is not an option, these are lightweight. We call them as lightweight containers. Okay. Whereas here, these are heavy weighted. They're weighted basically a lot. In basically the containers that we have, right? We will always use Linux operating system only. Okay, same guest OS, that operating system would be Linux operating system. Okay, that's also something that you should remember. So because these are heavy machines, right? Virtual machine, isn't it? So we are creating a separate machine. Though you have a choice of creating your own operating systems as per your needs, it requires more memory, right? Disk space, memory, right? So on the host server that we are using, we will be physically demanding for certain resources more than what we use here in Docker containerization. Docker uses less memory, obviously, right? You don't have operating systems and all that. It is very lightweight. Only application is there. Now, because it is a separate machine altogether, when you want to start up, when you want to boot up, this is time consuming. This is like flash of a second. It boots up in flash. It's only application, not the operating system is there, right? So it doesn't even have a glitch, just ready to use. Okay, so that is the boot up time. This is hugely different. Docker is super fast. Okay, and thereby the performance, obviously, because it's not a heavy, performance also is going to be better when compared to your virtual machines. From setup perspective also, Docker is easier. Right? All you need to do is bunch of commands. That's all. All you need to have is a Docker software and bunch of commands which builds and saves and pushes your Docker image. And when you want to use that, you just try to run that particular image so that a container is created. A container is nothing but a runtime instance. We call it as a runtime instance. It's like you have an image, take a snapshot image, and then you use that image for your operations perspective. So when you want to activate it, that's when you call it as runtime instance, right? You trigger an image to a container. Next. The Docker container has OS independence. Right? That is another beauty. You can take that image to any platform. All you need to have is just the Docker software installed. That's all. Right? Whatever the containerization software that you probably want to use, you need to have only that software. And irrespective of OS, it's going to work. Right? So these are some of the benefits. So you basically talk about less resources usage here. You'll see that it is fast. right? And independent of platform. Specifically, OS is what we talk about, independent of OS platforms. Right, so that is the containerization advantage when compared to virtualization. Next. Now, as we talked about some of the advantages of the Docker with respect to the setup and at a high level, right? We'll also talk about that as a developer, when you try to use Docker, you will be able to build right solutions, or you want to develop some applications, right? Solutions. You will be able to send that, right, as a developer, whatever application or solution that you're developing, you will be able to send it to tester. In fact, multiple testers, right? All you need to have is Docker running on the environment. So you're only taking the application and the dependencies as an image and send that image to the tester. In the testing environment, I mean, their environments, the only requirement is the Docker software, as I mentioned. So when you try to work on this image, we will run that image so that we get a container. This container is basically a runtime instance. We use this terminology. That means your application is ready to use. So we are taking a snapshot of your application and the dependencies, combine everything, and send that image to the testing environment. And in the testing environment, we basically have this Docker, which uses that image and creates a container runtime instance. And once this is created, here, the tester would be able to test the application. So there is no issue of environment dependencies, right? And the further advantages of Docker that we talk about is it is consistent to start with. So as a developer, when you develop the application, right, and once you create an image, that image is fixed and you can give that image to n number of different team members. It will be consistent, right? It will not change unless until you want to update your image, right? So that is one advantage. You will not see that tester one sees different application, test two will see different features in the application, right? So that doesn't happen. There is consistency here. Then they are isolated. Okay, these are completely isolated features. I mean, it is right. Nothing it has to do with other applications, or as we talk about independency, right? So these are something like an individual independent image or containers, and everything that is required for that application to run will be there inside it. So it is not depending on something else, right? There's isolated units. The entire process of deployment becomes very easy. So you will have fast or quick deployment, right? This is another advantage. So you immediately start working as a tester. You give the right, you get the application that you need to test in the image format, and you're going to containerize that, and immediately you will start right, deploying it. All you have to do is create a container and you'll start running it, right? So fast and quick deployment. All right, so that's another advantage. So a lot of things are automated. So you'll have automation achieved, right? And because you're going to work on these applications as an individual entities, independent entities, you'll also be able to achieve modularity. Now, the advantage of modularity means is that you can have multiple sub features developed by different developers as an individual features altogether, and then you bring them together into a single platform, right? Like you're installing multiple Docker containers, and together they'll work as a single solution, right? Microservices, you can basically call them as microservices. So modularity will allow us to break down that entire application into smaller pieces of applications. Right? So that's one advantage. Next, it is portable. Right? That is also another thing that we need to talk about. Irrespective of what operating system the host is using, that is the developer is using, irrespective of that, the container would work, or the image that we are using, right? The container would work in testing environments. Irrespective of operating systems, they work. Right? And the most important thing is scalability. In developers' environment, the application might have been developed in a smaller server, right? It's not highly configured. Hardware is very minimal, for example. But when you talk about testing team, there might be multiple people who are using the same hardware, or same application has to be tested by different testing team members. So in such case, the application requires a lot of resources so that these multiple testers requests can be accommodated. So the application that we are installing can be installed with higher configuration, that there is more memory can be assigned. Right? It is OS independent, it is hardware independent. It's just an application that we are getting. So I can ensure that the application is sitting on a higher configuration environment. So you can scale up, and let's say your development team is big team, but you have only 1 or 2 testers who are basically testing the application. Then you can also scale down, right? So there is a flexibility basically in order to deploy your application. So these are a bunch of additional benefits that we'll have with respect to Docker. Okay. So as a developer, right, you develop this application. There's some application that you developed. Okay. And this has been given to the testing team. So these testers that we are speaking about, there could be multiple testers, right? So it's not just one testing team member that we are talking about. We may have multiple testing team members. So when you're giving this, you have to basically give the image of the application. Right? As a developer, when you are trying to pass this application to the testing team, where you might have multiple testers, you're going to pass the image. Okay, remember that. But if it is not from an image perspective, if it is like a separate old technology where you're just giving the software that you have developed to the testing team, and while this is build 1, let's say this is the first release, but you still have the development cycle. So you further develop, right? New features are added. Some upgradation happened to the application. So I'll say app version 2. This is version 1. Now, again, what you have to do to this testing team, you'll have to pass this application to, and these people have to reinstall, reset up, right? Redo everything. And if these testing team have different systems, all of them have to do the same process again. Right? So the users, application users, it could be testing team, it could be the released product in production environment. So if you have multiple users who are accessing the application, whenever there is an update happening, all the users should get that updated features as well, rather than a manual setup where they try to uninstall this application one, reinstall application two, try to reset up everything. Rather than this process, can we not have an approach where, as a development team, you update your application, offline you test the application, and then push it to the production environment? Irrespective of what is the functional level understanding or technical level understanding of the end users, the application should automatically get updated. That's what we see in mobile applications. If you see, some application features are updated even without you manually doing it. Even without your knowledge, the application gets updated automatically. Right? As an end user, you don't have the headache to uninstall and reinstall it, isn't it? So the application users, a number of users, all of them should see the changes or feature upgrades. Now, manually, you don't want to update each and every application, right, at the end user. Even if you're using this application and containers are created, you don't want everybody's container to get manually updated, isn't it? Because these containers are independent, right? So you don't want the end users to take the pain of updating their end user container machines or container images. You understand the problem? Whether you're doing manually, whether you're using Docker, you basically give the application. And in the end user side, this application that we are using, right? The end user side, we will have the containerized runtime instance created by the end users for using that application. But managing those containers is the question that we are looking at. So if I make some update to my image, then does that upgrade also automatically reflect to all the users? If I talk about Docker level, no. So manually, end users have, all the end users who are applying using that application containers should manually update it. You'll have to convey the message to all the users saying that, hey, I have updated the image. Please refresh or update your container. You're manually conveying the information and people are manually doing it. And this is the problem, managing all these containers. Right? Now, this is where we need container management system. We want some technique which can allow us to do management of containers. And of course, you also, once we try and to talk about the maintenance, you also might want to track the performance of the containers, understand the health of the containers, right? All those things, right? Everything, basically from a maintenance perspective and operations perspective. So this maintenance challenge actually triggered a new software called Kubernetes. This was developed by Google, and the development happened in 2014, very recently. It's not that old. A lot of applications that we talk about are from 1990s, 1980s. Kubernetes is a very, very new application, right? So it's 2014 developed application. And of course, Google. Whatever we speak about, right? 90% of the applications that we are going to talk about are developed by Google directly or indirectly. Google's hand is that. Okay, so Google has invested their brain and developed a cluster of container, sorry, not cluster, a container management framework. Container management framework. Because if you have one or two containers, there is no problem. But when you're developing an application, you don't know who all are going to use that application, isn't it? Now just imagine that you are developing a mobile application and giving that mobile application in the Play Store. So a lot of people in the population, they are using that application. Would you be able to manually manage all of those containers or the applications individually? Not possible, isn't it? So that's where Kubernetes is required. And from our perspective, we are only talking about the application of Kubernetes from a machine learning perspective, not from a software development perspective, friends. But the idea is similar. As you have seen, I have not mentioned that the application is a machine learning model. Okay. So that's Kubernetes. Hope you have now got the fair bit of idea on what exactly is Kubernetes and why we need to use it. But in order to talk about Kubernetes, you need to get that Docker picture clear. There are various components in Kubernetes, the architecture, right? Kubernetes runtime, and how CI/CD pipelines are maintained in Kubernetes. So these are the major agenda points that we will be talking about with respect to Kubernetes. So Kubernetes, as we talked about, it's a platform to orchestrate the deployment. Orchestrate means trigger, schedule, manage the deployment, and the deployment happens on containers. So in short, it is a container management system, and it is an open source. So it is a platform which will allow us to deploy, scale, look into the performance, right? Whole and soul, we are talking about management of the containers. This is originally developed by Google. And the core functionality is to schedule the workloads of containers. And of course, as we discussed, right, it also ensures that the performance is tracked, failovers are monitored, the crash, right, container crashes are monitored, high availability is given. So these are other capabilities of your Kubernetes. So Kubernetes is, sorry? Somebody had a question? Okay. All right. So Kubernetes is basically not a platform. It's not a platform as a service. Okay. That's something that we need to remember. So container orchestration. These are only right slides which give you the definitions from the perspective of what we understood. So efficient packing of containers following the constraints of the deployment environment and the cluster configuration. Now, cluster, what does cluster means? Yeah, what does cluster configuration mean? Clusters means. Anyone?
Basically a group of many elements.
Exactly. Cluster is nothing but a group. Right? So here we are talking about containers. Application, individual applications, which probably are required for load balancing and high resource consumption environments. So you'll have a group of containers which are supporting the end user's request. So that becomes a cluster. Right? So that cluster configuration is also managed by your Kubernetes. As I mentioned, right, it also keeps a close watch on the dead, unresponsive, underperforming, or unhealthy containers. So automatic maintenance is happening with respect to the failures of containers. Benefits of containers, of course, there are many, as we have discussed about the container process. You have looked at, right, our mobility, portability, automation, flexibility, modularity, isolation, portability. So all these are the benefits of using containers. So we are basically taking those advantages. The containers in the cloud, right? So this is something that we will have to look at, and I will be talking about how the Kubernetes engines can be used on, let's say, GCP, and I'll also talk about Azure, and I want you people to work on AWS. AWS being the most popular cloud, I will want you people to explore this. I will be talking about how Kubernetes engines are used in GCP and Azure with respect to machine learning deployment. That is where our core operations have to lie. So I will be doing machine learning deployment. And this is your assignment. It's very simple, guys. Once you understand the process, you'll just feel that, okay, step 1, step 2, step 3, and done. Manually, you don't have to really do a lot of complex steps. Thanks to the evolving cloud platforms, everything is being automated for the end users, right? And when we talk about cloud platforms, you'll have unlimited resource access. So obviously, that's where you want to actually take the advantage of this automated container management system. You can scale up to hundreds of machines, right? Hundreds of containers. We call them as pods in Kubernetes. So the terminologies, components, I'll show you then, right? Then you'll understand. This is a very good comparison, pets versus cattle. If you are very, very fond of pets, probably you will have what? 1, 2, 3 pets, right? And you will be able to take care of these pets. You can give individual attention to each of the pet, and right, you could groom them, you feed them, you take care of their health, right? You basically walk with them, right? So there are a lot of things that you will be able to do if you have limited number. But when you talk about a cattle as a farmer, right, you'll have a group of pets, right? We call them as cattle. We don't call them as pets anymore. There is a group, probably 50, 100, let's say goats. Will you be able to give the same kind of an attention that you would give to individual pets to the cattle? No, right? Obviously, your attention span would be decreasing when you try to give that importance to each and every animal in this particular group of animals, the cattle, basically. This is the comparison. So here we are talking about Docker containers, individual Docker containers. But if you have many containers, obviously you want something which is automated to manage all of those images or containers. So that's a very good comparison, which should give you a clear picture on why containerization management is required. So Kubernetes concepts, if I talk about them, you'll have clusters, you'll have nodes, you'll have the master node, then we have the pods, then we have labels, annotations, labels, sectors, services, volumes. So these are some of the high-level concepts that we will have in Kubernetes. We will talk about the architecture and the components. You'll get a clear picture on what exactly these components are and what is what and all that. So Kubernetes has another short name to start with. It is also called as K8S. Kubernetes, okay, Kubernetes. So it's like pronouncing K8S, right? So Kubernetes, that's in short. So as we discussed, Kubernetes is basically allowing us to get the microservices going on. Microservices are implemented. So each service can be individually managed, right? That's basically the primary objective. So it's a framework or a tool which allows us to manage containers or microservices, you can say. These are different terminologies that are bringing up. Now, these containers, right, they can be distributed to different machines. They are not lying on a single machine. They can be working on different machines, right? And this Kubernetes is basically a platform which uses these different distributed components and tries to manage the life of, or you can say the development life cycle of your containers, right from its creation to its submission or dissolution. So through the entire journey of a container, Kubernetes is basically there to maintain it. Okay. So let us try and understand some terminologies in Kubernetes. But before that, right? So Kubernetes is basically, let me take these components, right? So these are your components that we'll have to look at. I'll talk about the Kubernetes components. But if you see, there are two primary components. One is the master, the other one is the worker or slave nodes. So this is your master here. This is like your master. This is worker 1, worker 2, right? So on and so forth. Distributed environment is always having or is always configured in master-slave architecture, where master is the controlling engine. It decides what needs to be done, who needs to do what and all that. And the slave nodes or slave components will actually follow the instructions that master is giving. Any distributed environment you talk about, it will follow master-slave architecture. Okay, so distributed framework, where we are basically saying that there we have multiple, you can say nodes or computers, multiple resources. They are working together for better management or better performance and better scheduling and all that. One of those nodes or one of those resources will act as the controlling or a manager for rest of all the resources. All right, so we'll always have master-slave architecture. And in Kubernetes, every machine that we use, right, as an individual machine, will have Linux operating system. Okay, these are machines with operating system automatically being there, which is Linux operating system. You don't have to install it. Your Docker container basically will be having those Linux operating system images. Now, these images or these machines, sorry, that we are talking about, these are nothing but nodes. That is the terminology, right? So we have nodes or nothing but machines. These machines are basically split into master and worker. And as I said, master is responsible for maintaining the state of the entire cluster. Cluster is nothing but group of nodes. This group of computers that we see. Worker node 1, worker node 2, right? So there are 3 machines which are interconnected. So it's a group, hence cluster. So master is responsible for maintaining the state of that entire cluster. The slave or the worker nodes here, these are ensuring that the containers that we are basically talking about are executed. So on that machine, you will have containers executed. Right? So this is how your configuration of Kubernetes looks like. And the different components that we are talking about, right? There are a huge list of components. We'll talk about that. Each of these components which are running on these nodes, this is node 1, which is master node. This is worker node 1, worker node 2, right? So these nodes have different services depending on whether it is a master, whether it is a worker node. Each of these components will have a dedicated responsibility. So what are these components and what exactly happens? We'll try and understand. So these are the various components on master node. These are the components and these are the worker node components. Okay, so we'll come back to this. This is how the interface looks like. Okay, we basically have, if I have to represent this, we will have, let's say, a client. I'm drawing that as a human being. This is your client. It could be a request from another application as well. This request goes to master node. Okay, it does not go directly to the container, it goes to the master node. And these master nodes will go and instruct the worker nodes, okay, to bring up the containers. Here you will have the containers, right? Here you may have many containers. You may have only one container or many containers. Okay, so that's basically the difference between your Docker and Kubernetes. Here, everything is packed together. Next, when we talk about this components, let me go there in the back. Yeah. So if you look at this, there is a clear segregation of the services that we are having on master as well as on the worker. So you can see the master components, right? API server, this is master. We have a database called etcd. We have scheduler, right? And we also have this control manager, right? These two are basically control managers. These four are your master node components. These are your worker node components. You have kubectl, right? You have something called as kubelet, right? I mean, kubelet is nothing but your representative. We'll have another engine that's not recorded here, but we basically have container engine, the actual container, right? So this container engine is creating the containers on the worker nodes. So we'll have container engine also, which is one of the component, and we'll have kube proxy. This is to ensure that there's kind of a network which is established between the containers and the master. So these are the 6-7 components that we will be discussing about. So when we talk about this API server, right, that is the Kubernetes server. Let me see if I have anything. No, I don't have that image. Fine. We'll talk about the individual components. So when we talk about this API server, that's the right, you say heart of the entire Kubernetes cluster. So when I talk about a cluster, I'll have master node, I'll have worker node 1, worker node 2. Right? Just imagine that you'll have this kind of a setup. You may have many worker nodes, but yeah, this is a cluster. Kubernetes cluster. So your API server will become the most important component, right? It is the heart of your entire cluster. This is nothing but a REST API, right? And this server will not have any state. It's also called a stateless server. And this allows, this API server is basically the edge point. It allows the interaction from the external world. Now, any application, generally, when you talk about external communication, that is HTTP or HTTPS communication, you basically either have port number 80 or 443, right? Remember, by heart these port numbers. These are default port numbers which are used for communication over internet, HTTP protocol. But just to ensure that these ports are not touched, in Kubernetes, we use a different port number, that is 6443, right? So 443, and this is 6443. Okay, so, and this is basically the default port which is used. Right, so the REST API that we are talking about, it listens at 6443. And within this API server or Kubernetes API server, we will have different subcomponents that we need to look at. These are the resources that we will have. Those resources are actually mentioned here. You'll have pods, right? You'll have the services, volumes, annotations, labels, right? All these things are additional resources that we have within the API servers. Okay, so these are the kube server subcomponents that we will have to talk about. Okay, all of these basically are used for managing the containers. Everything is for container management only. That's all. So you'll have network policy, predefined network policies. You'll have replica set because you need to try and have to scale up, for example. So you'll have pods which needs to be created, and within the pod, we'll have to give the mapping, right? And so there will be group of pods which will be like identical pods, right? So replicas will have to be created. So we'll have replica set. You need to have some kind of a persistent storage component. So that is also part of the resource. So all these are the resources that we have in API server. At a high level, we are not going into the very much detailed discussion of all these components, but these are some of the components that we'll have in API server. Then we have etcd. Now this is the component that you'll have to basically look at, because this is your data storage for your entire cluster. So everything that is basically happening in the cluster with respect to the operations, with respect to the maintenance tasks that we are seeing, all of that information is getting stored in this database. This is a NoSQL database, right? And this is your main storage or memory for your entire information in the cluster, right? Main memory. Now, this has nothing to do with Kubernetes. It's like you have a Kubernetes engine and you'll have a database. Right? It's like something which is sitting outside. We also call it as an independent project of Kubernetes. Unfortunately, the Kubernetes development did not focus much on this component, etcd component. So you don't have any alternatives. By default, etcd database has to be used. Right? This is the only NoSQL distributed database which will be used in Kubernetes, no other alternatives. Right? So every API server call, for example, right, requires some data to be either written or accessed. Right? So that happens through etcd only. Right? Any data information that, data that you require is in etcd, whether you write or read. So read-write operations happen to etcd. And this is your metadata, right? It basically contains all the metadata for your cluster status also. Which nodes are up, which nodes are not up, which pod is working, which pod is not working, right? All that will be there. And though it is an independent component of your entire cluster, Kubernetes cluster, if this is crashed, then there is no communication of any sort of information. So your cluster becomes inaccessible. So if you remember, if you are familiar with Hadoop and all that distributed framework components, then in Hadoop also we have something called as single point of failure. We call it as single point of failure. So in distributed environment, if one node is crashed, you'll have some alternative, right? If your one worker node is crashed, you'll have other worker nodes coming into the picture. But if etcd is crashed, because it is the single source, there is no backup or no alternatives. If this goes off, then your entire cluster gets inaccessible. Hence, it's called as single point of failure. And another drawback of etcd is it is disk-based storage device. So that means the database uses disk for storing all the data. There is no memory component at all. So that means it is going to take take time to access the data, work on the data, retrieve the data. If it would have been in memory, then the performance would have been much faster. So that is another drawback, right? This is basically depending on storage disk of your physical machine that we are using. Okay, so that's the another point with etcd. Next, we have control manager. So as you can see, kube control manager or control manager, it maintains and contains replication. Replication means if you want multiple containers to be brought up, then the duplication, the copy creation is done by your control manager. You'll just let control manager saying that, hey, I need more images, replications. So it automatically creates that. It controls the pods, it controls the services, the endpoints, and all those things, right? So control manager, in short, is trying to maintain the state, the actual state of the cluster, and it communicates with etcd. So whatever is there in etcd, it tries to maintain those states, right? And it manages these pods, nodes, services, right, on the cluster, which basically are running. So the information, the states, the statuses of all these components, right? Everything is collected by control manager, and using that and etcd status, the control manager is trying to maintain the state. All right. And the controllers, basically you'll have some of the controllers. These are like predefined scripts, you can say. So there are certain controllers like the node controller, endpoints controller, the namespace controller, right, etc. These controllers are readily available, right? And these controllers are like scripts which will be internally called to maintain the state of your entire cluster. Now these control managers can be on different, I mean, basically you can customize those control managers to manage the resources that are being run. So these cloud platforms that we are talking about, they have their own control managers because they are dealing with their own resources, right? So you have GCP control manager, AWS control manager, Azure control manager. So depending on the hardware that you're basically setting up your cluster, Kubernetes cluster, you'll have those dedicated control managers. Then comes the scheduler. The scheduler is responsible for assigning a worker node. Okay, there are many worker nodes. Scheduler is checking the status of these worker nodes, and it is selecting or electing one worker node. Right? Scheduler is responsible for that. And to do that, scheduler will continuously keeps checking with API server. Scheduler will continuously keep checking with API server to check what are the list of nodes or pods that have not been scheduled and are available. Right? And each object, each pod, we call it as, that information is there in etcd. Right? So with the information from etcd, your scheduler will be able to assign name to the worker node. Right? So pod is like runtime instance. Right? And the etcd has that information basically. And if a pod is given a name, we basically call it as node name. If you have that node name given, right? Basically, this is nothing but the worker node. So I'll basically say, hey, this pod has to run on this worker node. Right? That information will be stored in etcd by API server. Right? This is the main engine. So it checks with the control manager to get the status of the worker nodes and the pods, and then it assigns a pod, which is nothing but a working instance, to be run on a specific worker node. So pod is given a name, runtime instance is given a name, we call it as node name. Let's say worker node 2. Right? So this scheduler will check the status of the worker node and initiates that pod on the worker node. Right? And it basically it's nothing but we'll deploy the pod on that particular worker. And scheduler is also responsible for assigning the name of the worker node for each pod. because it is constantly keep checking with API server on whether the node is available or not available, right? So basically using that information, it will say that this worker node is free. So right, it's always in touch with API server, the service. The scheduler service is always in touch with the API server. So the handshake of information is happening, and scheduler is basically updating the name of worker node via API server. Right. So these are basically the management components. So using this, all the management happens on your Kubernetes cluster. Then if you talk about the worker node components, you'll have 3 components, not just 2, but you'll have 3 components. The first component that we should talk about is kubelet. And this is the important component on the worker nodes. This kubelet service, this component interacts with the local Docker instance on the worker node. So you'll have a cluster, you'll have a master, you'll have these multiple worker nodes, right? Depends on capacity of your cluster. You may have 2 or many worker nodes. So this is like a separate computer, right? Worker node 1 is a separate computer. Worker node 2 is a separate computer, right? So each of these worker nodes will have Docker instance setup. Even Docker software is already installed on these worker nodes. So this kubelet service is checking with the Docker service, which is installed on the worker node. It directly interacts with that Docker software, right? And this kubelet is like a service which is run on the host machine. Okay. There is some configuration files and all that. We will basically, your kubelet refers to the .conf file, kubelet.conf file, right? And all the configuration related details will be there in the file. Okay, and there are 2 important things that kubelet will be updating. One is the endpoint, right? Endpoint is basically how your end users can communicate with the application that you are developing. But this is with respect to the kube server component, right? Kube server is like your API server that we're talking about, right? So communication with respect to the kube API server is what is updated in the conf file. Right, and the other one is the Docker details will be updated in the configuration file. So you can see that the communication between the local Docker software and the API server on the master, right? So for communication, this kubelet is like an interface between these 2 applications. It acts like a bridge of communication between these 2. Because ultimately, if I have to create a container on the worker node, I need Docker server. Unless until I instruct the Docker server, the containers are not kicked, right? So API server will directly communicate with the Docker software, which is there on the local machine. That is this worker node. Okay. And this kubelet is constantly checking, right, the information. So it's like there is communication happening, or there is some kind of an information exchange which is continuously happening, and kubelet is responsible for that. It is said that it checks with an interval of 20 seconds, right? It keeps checking for the list of pods that are getting updated in etcd. So in etcd, the information about the pods is the runtime instances. Pods are updated. So kubelet will communicate with etcd. Remember, kubelet is etcd is like a separate entity. So this kubelet will be communicating with etcd database to check if there are any pods which are updated. These pods are updated by scheduler in conjunction with API server, right? In tandem with API server. So once the updated information is there, then Docker, the kubelet will update that to the Docker software, right? It interacts with the Docker software, so it keeps updating that Docker daemon. Right, so that's basically the task of your kubelet. So it also, as I discussed, right, it also keeps checking various other informations like how many images are there, how many containers are created on those images, which of them are being used, which of them are not being used, right? All that status information is also communicated or captured by your kubelet. So this kubelet becomes very important. Without kubelet, you'll not be able to create your containers. Right? Then we also have this proxy and container engine. So if I talk about container engine, now we basically talk about the Kubernetes software itself as the container engine, right? I mean, it's a management tool. So your containers are basically managed by this container engine, and which is nothing but your Kubernetes software. And in Kubernetes, in order to manage the containers, by default, we will use the Docker software. Docker is used to convert that image to a container, right? So by default, the container engine, which is managed by Kubernetes, is Docker software, right? And you can also use different services. Like we have something called as containerd. That is also another service similar to Docker. We can also use that. There are other applications also which can be used for containerizing your applications, similar to what Docker does, but Docker is the most popular right software. For example, if you talk about potato chips, what is the first thing that we get in mind? When you talk about potato chips, friends, what is the first thing that we get in mind?
Place.
Exactly. It doesn't mean we don't have other manufacturers, but Lay's has captured the market to such an extent that we kind of refer the name of Lay's to refer to potato chips, or when you say potato chips, it is referring to Lay's, right? It has owned the product, right? That in such a way that it has created its own image for that particular product. Similarly, Docker is one of the softwares which is used for containerization of your images. To such an extent, it has grown that we kind of use Docker for representing containers, and containers means Docker. But we do have other softwares also, which are probably right very rarely used, unless until you have some challenges with Docker or somebody wants to try something different. We generally don't go with other softwares. One of the software that I'm talking about is Container ID. Containered, not container ID, containered. And we also have something called as, I think, CRIO. Might want to check on this. Different container softwares are there, right? But Docker is one thing that we will refer to. We don't talk about anything else. Then comes the proxy. We also call it as kube proxy. This proxy is the component which simply handles the networking. Any network related task that we talk about on Kubernetes nodes, worker nodes specifically, right? Because that's where your containers are actually getting deployed, will be managed by this proxy service, right? And it allows the access to the running pods, running containers, to communicate with other containers, other pods. In fact, as an end user, if you want to access any application which is running in the runtime instance, that is your pod, then you need that network communication, right? Network establishment. So proxy will allow external applications also to be communicating with your applications which are sitting in the pod, right? And these proxies, kube proxy basically is having a something called as service. The feature name itself is called as service, right? And these services are ensuring that the traffic the communication that we are basically network traffic, right, is routed to the pods, the respective pods. The service handles that. And in short, your proxy is used to maintain certain network rules on the worker nodes to ensure that there is proper communication with external applications or pods, internal pods, right? All that network related communication is maintained within the rules that are defined. This is something your administrators probably or your business requirements will come in picture to define those network rules. But once those rules are defined, proxy will maintain that communication happening. So these are all different components that we have, right? And you can basically look into these components in detail, probably at a later stage. As and how you start using it, you kind of get the familiarity. Right, so this is basically how your container runtime interface runs. So kubelet that basically will communicate with your server, API server, and that API server will ensure that the container images are running on the worker nodes, and worker nodes will have the local Docker installation setup, where kubelet is indirectly communicating with the Docker software to ensure that the containers are triggered. Right, so this is how basically your interface looks like. And we basically call this as gRPC, remote procedural call. That's the full form. It's basically one of the frameworks which is used for having the communication established between all these individual independent microservices. Microservices, because these services that we are trying to work with are individual independent modular services, which all together try and give us the end result. And each of these individual independent service is again having failure mechanisms and self-maintenance and all that. So that's the framework which ensures that all subtasks or sub-services, microservices, are communicating among each other and giving the end user the required experience. Okay, so this is a little advanced detail. gRPC is a protocol which is used. I mean, it's basically the communication interface, more into networking and all those concepts. So this is a typical CI/CD pipeline that we will basically have. All right. Okay, so this is basically the theory, not much of theory here. In order to install the Kubernetes service, right, we will not be able to do it on our local machines. The complete Kubernetes engine cannot be installed on our local machine. So we will be using something called as Minikube for installation. And it takes some additional configuration, some other additional softwares also, like VirtualBox is something that we will be installing to create the cluster of machines that we need. So virtualization is used to even work with your Kubernetes, because we need to create multiple worker nodes and all that, right? So for that, we will have to create the virtual machines and try to replicate those virtual machines as different computers which are interconnected. We are creating a cluster like master node, worker nodes, etc. And using that virtualization, VirtualBox software, we will install a software called as Minikube. It's a smaller version of Kubernetes engine, you can say. And then we will also be using the Kubernetes engine or Kubernetes services on cloud, as I already mentioned. Okay, so this is basically how we are going to now practice the installation of Kubernetes. All right, so we will take a small break. We'll come back and discuss about the installation of the Kubernetes services. Okay. Yeah. Okay. So we'll take a break, friends, and post the break, we will talk about the installation. It's 10:24. We'll connect at 10:34. 10 minutes break. And yeah, we'll start with the installation process. All right, friends. So welcome back after the break. So just a quick turnaround. We basically were talking about virtualization. But virtualization has certain problems. It is heavy weighted and heavy resource consumption approach to ensure that the applications are shared, the developed applications are shared with end users. So this is the containerization concept which came into picture, which is like a lightweight application perspective virtualization. Right? Only applications are getting virtualized or containerized. There are a bunch of advantages that we have talked about when we talk about containerization. And this containerization is done using a software called container. And when we talk about the advantages with respect to the containers, we have portability, consistency, then performance, right? Wise quick performance as an advantage. Then we have modularity, scalability, right? All these bunch of advantages are there with respect to creating containers. And in order to do this management of containers, we will have Kubernetes used, which is also called as K8S, shortening. And Kubernetes is a container management open source software, which was developed by Google in around 2014. So if you have less number of containers, then Docker is good enough and manual management of your containers can happen. Runtime instances. But when you have a lot of containers to be managed, then we need an automated technique, which is Kubernetes. Right? And when we talk about Kubernetes, Kubernetes has a bunch of components which allow the containers to be managed. And Kubernetes is a cluster-based distributed computing framework, distributed framework-based application. So it will always have master-slave architecture. And in master, we will have certain services. We talk about API server, right? Then we have etcd. Then we have scheduler. And we also have control manager, right? So control manager. These are the manager or master-based applications. Then with respect to the slave, we have kubelet. Right? This becomes very important interface between API server and the Docker, local Docker software, Docker service. Then we have proxy, which is basically used for network-related maintenance. And all this is done using your container engine. And here in Kubernetes, the container engine that is used is Docker itself. Okay, these run on slave or worker. Right? So this is about your Kubernetes. And when we talk about the Kubernetes, as we discussed, it is running on the port 6443. Right? And everything is automatically managed. So when a client is making a request, it goes to the master node, and this master node communicates with the worker nodes to get the containers. And these containers will have proxy service, which allows its end users to have a communication. Network establishment happens here. Okay, so this is a typical flow of requests that happen in the Kubernetes. But in order to run these Kubernetes engine or Kubernetes service, we need Docker service to be understood first, right? So containers have to be created and all that. So let's install Docker first. And very important with respect to the containers, it will automatically have the Linux operating system. Each container will have dedicated Linux operating system pre-installed, right? So we don't have to set up operating system, and all the dependencies that are required for your application to run will always be packaged together in the image. So all those dependencies will also be set up onto your container, right? And that will ensure that your application is up and running. Okay, so that's basically how your Docker works. So let us start with Docker installation first. Okay, so for that, I would open browser and I will say Docker installation. Docs.docker, right? So this is your Docker official documentation. We can go to this Docker official documentation. And depending on what operating system you are using, you can click on that respective operating system for setting up your installation. Okay, this is the installation overview, and we are basically talking about Docker desktop for Windows. Very, very simple steps, friends. You can just ensure that right, these steps are followed depending on what installation that we have here, right? So just follow this. You can also have this Docker desktop, right? We'll look into that also. But in order to ensure that your Docker is working, right? One of the softwares that we need is this Hyper-V. Okay, this hypervisor setup is required. Okay, so you need to look into that aspect as well, and you need to right, follow the instructions here. It's just you get a .exe file, right? And from here you can just download it and follow these instructions. So you double click it, click next, and it will basically give you this option. Once the option is coming, you will basically say that WSL2 instead of Hyper-V option have to be selected in the configuration. Okay, and then just follow the installation steps which are given on the GUI, and you complete your installation. Okay, very simple installations, guys. You really don't have to worry much. Once the installation is completed, you will get Docker desktop. Okay, so when you're installing, you'll also get a front-end application. And one more thing is, you will always better to have Docker Hub account created. Okay, there is something called as Docker Hub. This Docker Hub is the I should say it's like the centralized repository, hub.docker.com. You will have to create your account here, register for this and create an account in this, so that any image that you are creating, which is on your local machine, by the way, can be pushed into this repository. This is a global level centralized repository which maintains all the images that can be used by anyone. It's a public portal. If you make your image public, anyone can use that image and then create their containers. Right? So this is like a centralized image management repository. So you build an image. If you want to use that image, you run that image in your local machine to create a container, which is something that we are going to demonstrate now. We're going to work on that. But if you want to save this image, then you can push the image into this Docker Hub. Open the Docker Hub, register, and sign in. Okay, this is the centralized repository, friends, as I said. So huge, millions of right? Applications are there here in the Docker Hub. Right? And once the Docker is installed, you'll also have I don't remember that this is sign in. Yeah, it's already saved on my browser, so it's automatically coming in. I just logged in. Right, so this is Docker Hub. I go to the main page. Let me see if I can. This is my repository, my organizations. Yeah, these are all the publicly available right images. You don't need to have an account in the hub to use the publicly available images, but just to maintain right a dedicated account, it is always good to have your account created right now. I'll also right. I mean, we will work with Docker on your command prompt, right? Or you can also use Docker desktop. Once the Docker is installed, you get this Docker desktop as well. From Docker desktop also, you can directly connect to your hub. You can see sign in right here. You can use your Docker hub credentials to sign into your account. And this desktop is basically a graphical user interface application, which allows you to see the images, the containers, if you have any, the volumes that if you might have created, right? Volumes is basically for your data storage and all that. Right? So from that perspective, you can also have external extensions and all that. For now, we'll only use this containers and images tab. So any container that you already have or you might want to create, you can basically refer to those from here. Remote container, remote repositories is when you connect to your account. So you can just sign in and connect to your Docker Hub account, and there you might have your repositories readily available. Image, basically image is nothing but a software that we want to use. All right, so just follow these steps, friends. And yeah, let me know if you have any challenges. Right, and these are the system requirements. By default, you will have right, these softwares. If you don't have, then you might want to install this. Windows 2, right, backend requirement. If you don't have, then yeah, you can just download and install this right application. If you want to use Hyper-V backend, then these are the steps. Any one of these options can be chosen, friends. You don't have to restrict yourself to use one of any one of that, but yeah, you can just basically right, use one of these. I remember I have installed sometime back. Yeah, I just followed these instructions. Yeah. Same, same folders. Let me know if you are having any issues in installation. So to start with, as I said, download this .exe file. Right? When you click on this option, download Docker desktop for Windows, you'll be able to get to work with .exe file. Double click that, and you will see all this. Let me see if I have this already. And I don't have this. Yeah, so this is image.exe file. I'll just click on this. It's already installed in my computer. I'm just showing you how the interface looks like. So my version is a little older version because I've installed it some time back. It says, do you want to replace it? Right, so I'll say no, at this stage, I don't want to do copy installation. But when you do it, it goes into the UI, and then from there, you can just follow the steps. Anybody is doing, if you want to share your screen. Is anyone installing or already installed?
I think I'll try later.
Okay. No, it's just that I wanted to ensure that the recording is done because my installation is already done. I cannot share the steps. So if anybody is doing right now, we can share your screen and record the steps. From that perspective, I was asking. Okay, fine. So I'll assume that you have installed, and let us try and run some steps on Docker. Docker has cheat sheets. You can also get those cheat sheets directly from the website. But these cheat sheets are already shared with you. This is the cheat sheet. These are all the commands, right? Typically, we will do this. Build your application image, build an image using the Docker file. Right? You will have to go to the current folder, and then you have to have all these files ready, and then you have to build your Docker image. Then if you want to share image, you can basically push the image to the repository. That is Docker Hub, right? So it goes and sits on your Docker Hub in your account if you want to push it. If you want to use something which is already there, you have to say pull. Build is to construct your local Docker image right now. And then once the Docker image is created, or once the Docker image is available, in order to create a working environment, you will have to say run. Docker container run. Runtime instance will be created. And so these are high level 3 steps that you will have in Docker. So let us try and check that. These commands are also given. Is this example? Yeah, this is one of the examples which is already shared. I think Docker commands would be there somewhere. Okay, fine, no problem. We will try and run these steps. So I'll go here and I'll say Docker. Because Docker is already installed on my system, when you say Docker, it gives me the instructions, right? This is like basically you're doing a wrong command and it is like help. If you want to specifically know the information about any specific command, here you can do this. Docker that command help. Okay, or you can just type this. Right, like this. Just replace your command with whatever the command that you want to run. All right. So this is basically the syntax. You just say Docker and then command. Okay. All right. Docker space images. This will list out the images if there are any. So if I go here, you will see the definition. Images, yeah. So Docker images. So Docker space command. This will list out all the images, and for containers, we have something called as PS. Yeah, list containers. Pull and push are there. These are basically to pull and push the commands, the Docker images from your repository. And for this, you'll have to, of course, log in. You can just say login, Docker login, and you'll be able to connect to your repository. You need to give your username and password on the command prompt to connect. This is to build the image. We'll run this now. And we'll try to construct an image. Okay, let's see if I have that basic Docker creation steps. Okay, it doesn't have basic steps. I think I do have something here. Do I have something here? That is also a little advanced. Fine. So we will try and pull one image which is available here on the screen. Yeah, so these are the images. See, very simple steps. So we will basically try to pull one image directly from the public repository. So if I want to see what is this, you might want to go to the hub, Docker hub, and search for Ubuntu. Ubuntu is a Linux operating system, right? And we are creating an image for your Ubuntu. So Ubuntu is a Debian-based Linux operating system, open source basically. So if you go into that, this is the repository, and we are trying to set up a Docker image using this Docker pull Ubuntu command. Right, that's the command you have basically seen here. Latest is basically the tag name, or you can say version name, repository, and the application. Okay, so I'll just copy and paste it this. You know, if you don't want to use that colon latest, that is your choice. And what it does is it basically takes the image, right? It is total size of 30.43 MB in your repository. It is downloading that image, this particular image, right? We have these different documentations. You can try and read that. So you'll have a software which is put here, and we are trying to download the software onto my local machine, right? That's all. It's basically doing that. So Docker is your application that you have developed or somebody else has developed, and we are trying to set up that Docker image on our local machine. Yeah, it's done already. Okay, so newer image from this particular location we have created. This is the location basically, right? So if I again say Docker images, so here when I did Docker images, it was not showing anything. Here I will say Docker images again. Now you can see this is the repository and the tag name is latest. This is the image ID, and this has been created just now. Created is 2 weeks ago because probably right. I might have used the same image previously some time back. All right. So that's recorded in my system. So it's basically showing 2 weeks ago. Okay. So this is your official image, and these are the various tags. So you basically see the tag. You can see this is something which is pushed 15 days ago. And some updates have been happened recently. So that is also something which is basically shown. All right. Now this is a Docker image. You can come here in the desktop and you can see under the images, the image that we just have created is shown. Okay, and you can see created 15 days ago. Right. So that's basically how we can create an image. Now this image is not active. I mean, it's not running, right? We did not create a runtime instance from this image. So we will be able to create that runtime image as well. So all you have to do is run. Either you click on this run, and when you do that, it creates a container here. Right now, we don't see any container, right? But when you do this, a container instance will be created, or we'll stick to this right command line interface to run the instance. So you can see this is the basically the command to create a runtime instance of your image that we are using, right? So either you can use the front end or back end. So if I click on this, these are the various options that you have. You can give a container name, right? You can also give the host volumes and the environment names to basically give. Or I'll just, as I said, I'll use this default option, container run, right? And create my Ubuntu instance here. I'll say Docker run. What is the tag? Run a command in a new container. Okay. Okay, let me see the shortcut. Here, Docker container run. You give the name. Let me first start with this. I forgot. So I'll say Docker PS. When you say Docker PS, it lists out the containers which are running. List the containers. I don't have any containers right now. Right. So we'll have to try and create a container, right? So let us do that. And as you have seen, we have to basically say Docker run. And then we need to run the Docker. You can basically give the port numbers and all that. I'll just simply use this command and I'll try to run the Docker image. Okay. So you have to remember the, sorry, it did not copy. I'll just type it. Docker run -p. Yeah, -p. That's the port number. And I'm exposing that to, let's say, 5000:5000. You can put any port number. And what is the image that I have? Ubuntu. You can also put in. Where is it coming with this? Good. I'm running the instance. Strange. Why is it not running? Let me just check. Why is it not running? Mhm. Mhm. No, this one do I have? Yeah, this example is already there. But this is for a machine learning. Why is this Ubuntu not working? Let me just run this without port number. Docker container run options image. Yeah. If I go to the official documentation, this is the pull of image. We have pulled the image and we have all these updates here. Strange. This is what we have done. This is to pull the latest of the image. What does cheat sheet say? Container from Alpine version image and running the container web exposing port number 5000 map port 80. And this is the run. This is what we have done, right? Let's copy this. Docker container run. I'm saying hyphen name. Right? I'll use the same name. -p. Exposing this, let's say 80 only. Image name is Ubuntu. Tag is latest. Why is it not running? Let's use the front end and see if it works. Okay, I'll just run it without any name. Oh, it's already running, but it is not able to start. Is that? Let's start this. There seems to be some issue in the image. This is what we have recently run. Okay. So the containers are starting, but because of some reason, it is not able to stay. This is what we have recently done from the command prompt. This is basically what we have done. It says in use. And these are the services which are used. Fine. So we'll not waste our time here. We'll move on. We'll try and deploy one of the local machine learning model that we have, and then see how does it work. Okay. In the last session, we have discussed about one of the machine learning model that we already have. Right. So let us try and look into that. This is the Docker. This is the image. And this is my repositories. So this is a repository that I already have, right? And I don't have any image updated into this. I can also push my image. I'll try to show you that, right? And then we will see how we can use that image in deploying, right, for usage, right? End user usage perspective. So for that, I need to go to model. This is our machine learning model, right? This is basically the right Docker image. Okay. Whenever we try to work with the Docker images, the mandatory things that we need to have is the requirements file. Let me open the requirements file here. You can see in this particular application, I'm basically just added all the Python libraries that I probably will be using. I just pushed everything which are required. If your application is a very small application, you don't need so many dependencies. But these are all the libraries that you need to have for your application to run without any issue. Okay, so this is the requirements.txt. We keep updating that. Then we have this Docker image, a Docker file, which contains the instructions for your Docker application to work. So you will have the command. We are basically saying from Python, that is the version 3.8 version is what I want to use, and I'm exposing this application at port 80. Expose this application to port 80. The working directory, you can give any working directory. Remember, a container has Linux operating systems. So under the current working directory, the home directory, we are creating a folder. So you'll basically have /home/ the username, whatever the name that you want to have. This is where is your working directory. Under this, we are trying to have a folder called flask-docker. You can give any name, your choice. And once this folder is created, we are instructing the Docker image to copy the required files. Requirements.txt. So we are first doing the copy. And then we are ensuring that the environment is updated. So we are running that script requirements.txt, which will ensure that all the libraries that are required are updated in our environment. Then we are copying everything from this folder to the Flask drive, right? Copy.
Hey, Sharad, question. So
Yes.
Which one is the image here?
Image? No, we are creating an image. We have not created an image. We are going to create an image using the script.
Okay.
See, there are, okay, let me explain the files here. So when you talk about machine learning model, you're probably developing your code using .py or .ipynb. This is your Python script or notebook. This is where your ML code resides. In our case, this is the file. Here, I'm having a multiple linear regression. I think I've discussed this code, right? Already in my previous sessions also, I've shown you where we are trying to predict the fuel efficiency, right? Mileage of a car. Some sample machine learning code we are using. It could be any code. It could be a machine learning code. It could be a deep learning code, whatever it is. This is your ML code. Now, when you run this code, you will have a pipeline implementation. Always remember, pipeline implementation is mandatory for productionizing your machine learning algorithm, right? So using pipelines, we will save the best model, right? This best model is saved using either pickle or joblib files. Okay. These are the Python libraries. So when you do that, you get pickle file, and this is the data pre-processing file. If you remember the code which we discussed in our previous sessions, we had data pre-processing pipeline. I'm calling that as column 1. And this is the best model that we have trained. So these are important. This code is not important for us. These are important. Okay. And in order to use these saved models using a web UI, here we are using Flask application. Okay, that Flask application is here, app.py. This code is also required. So I'm using 1, 2, 3. These 3 are from your ML model perspective, right? Pipelines, saved pipelines, data pre-processing pipeline, and the best model. You both these both can also be saved into a single pipeline also. That's basically from an ML model development perspective. In our case, I have 2 different pipelines, and then I have Flask application code. Right, I'll show you what exactly happens here in the Flask application code also. I'm saving it in the notepad, sharing it in the notepad. So we are importing Flask and the rendered template application, and we're creating an app here. And you can just put this app somewhere here also. Okay, like this. This is our application. Okay, you can put this here as well. So these are basic Python requirements. We are importing the libraries and we are importing the saved models, loading them into the environment. And then this SQL Alchemy is to ensure that we connect with the database. Here I'm commenting it. I'm not using this database connectivity thing. I just commented that. And then we have the Flask application initiated. This is the initialization. Instantiation happens here. And when you are trying to connect with this application, by default, it goes to the /. So it's like your website, right? So your website will have host : port. This is the address, and you'll have /. This is the home directory or home page for your portal, web UI. So when you're coming to this location, this is the landing page. You are basically saying render this template and give the experience to that particular end user. So we are defining a function called home, and this basically is calling the function, returning the rendered template, and this HTML document has to be executed. That HTML document is also there here itself. Always in Flask, we use the standard folder names. Templates is the standard folder name inside which we need to have the HTML page. So again, I'll show you the HTML document here. It's a simple HTML document. We'll have mileage prediction, right? Basically some kind of a text, logos and all that. And this is where we are passing the input. So input type is a file. We are passing a file to be loaded. And once the file is loaded and once the action is happening, submit button is created, it goes back. It returns back to the submit page. So if I go to again this file, here when we do the action, it goes to the /success page. So when you come to the /success, we are triggering this particular function. So in success, it takes the details of the input file that is getting passed, uploaded, right? And we're converting that into a NumPy object and then doing the data processing. CT is the data processing pipeline. So I'm transforming the data using the CT. And then I'm doing the predict using the model that we have uploaded here. This is a trained model, right? So using the trained model, we are predicting. We get the results which are converted into a data frame. And this data, this is basically getting added to the original data itself, right? And we are basically printing that result. Okay, so that's all we are doing. These lines are commented. These are used when you want to push the results into a database, right? So I've commented the database details, so I'm not connecting to the database. Hence, I'm not pushing anything to the database. These lines are commented, right? So that's basically how your application runs. I'll not say anything. I'll just come out of this, right? So Now for Docker image to be created, I will take this, and this. This code is not required. Remaining everything is required. From an ML model perspective, we need the pipelines, right? These are ML model related files. Then from Docker perspective, oh, sorry, this is also from a deployment perspective, right? Web UI perspective. I'll change the color so that you understand. Web UI perspective, I will take templates folder and app.py. These two will work always together because web UI will need these saved models. Then from a Docker perspective, I need the Docker file, Docker script, and the requirements file to ensure that the dependencies are updated. Right? So these are the three set of objects that we are using. So the Docker will take these files using the dependency files. It will first set up the environment and then puts these content into that environment. This will give us an image which can be run in any server, anywhere, right? I mean, any computer, basically. All you need to have is the Docker software. That's all. Right? So this is basically the deployment stage. To deploy, we are basically giving these instructions. So command is using Python 3. You want to run the Flask application and host it onto the local machine. 0000 is your local machine. So when you do this, this is basically like the edge point. We are creating the endpoint here. So what is happening? From Python, where we are basically trying to use this Python image on the Docker image, where we are exposing the content onto the port 80. We are creating a folder called Flask Docker. First, we are copying the requirements file and ensuring that all those dependencies are installed, and then copying everything into that folder. Once everything is copied, then we are executing this to ensure that the image is getting executed. Image is nothing but ML model, right? And that script gets executed here, and we get the end outcome, right? So this is your script which gets executed at the end. All right. So in order to do this execution, always ensure that we go into the directory where this file is. Okay. First, we'll have to go into the directory. So I'll say D:, and then I'll say CD, copy the path and give it. So you can see these are our files, right? I will show you what exactly happens on the end user perspective. If you run this machine learning code on my local machine, then what is happening? So I'm first running it on my local machine. In order to execute this Flask application, we basically say Python app.py. That's all. Why? Install Flask. It basically says that my local machine does not have Flask application installed. That's the reason I had to install Python Flask application first. Yeah. See, once you execute it, it basically creates the runtime environment and we are getting the host. So I'll use this quote. And this is the web UI that we are seeing. And I will just open. Go to the location where I have this test file. I don't have the test file here. Very good. Yeah, I have the test file here. I just select it and then submit. So this mileage is the output, predicted output using machine learning model. right? So this is how the end user will see, right? You can see here, this is slash. And when I click on submit by passing this data in the backend, the action is getting triggered and predict function is getting executed because it is redirecting to slash success page. And in the success page, these output is getting printed. This is on my local machine, right? So I'll just cancel this. I'll close this and I'll come out. Okay. Now, in the Docker, I'll be running this. So first, I will have to create an image, right? Build function has to be used. Where is this build function? Let me use the commands. Fine, where I have. Yeah, this is the build function. Okay, so build the image. So for building the image, this is what you have to say. I'll change this name anyways. I'll say Docker build -t. I'll say MLR cars v1. I'm tagging our image is v1. The repository name is this. I'll say v1 directly. Yeah. So dot is where my location is. So my image name is MLR cars v1. The content is in my current location, and I'm trying to build this image. So Docker build -t image name dot is the current location where I have all these files. So you can see it's basically copying everything, setting up everything, right? pip3, this command is getting executed now. All the copying has happened. It's taking time to build all these requirements that we have, right? These are all the applications that is getting copied. Exporting the images and done. So image is created. This is in my local again. So I'll say Docker images. You will see Docker images created. Now look at the size of my application. Because it has model, it has saved trained model, it has Python application installed with all the updates, right? So it basically has 615 MB file. So you can basically try and check all this. Storage space. So if you look at the files, individual files, this is only how much? 86.5. But when you are implementing it onto the Docker, all the runtime instances are getting executed. Python software is executed. These libraries are executed. So total size is 615 MB. Right? Now, this Docker image that we have created is on our local machine. Okay. Unused. This is not used yet. Okay. Now I want to push this onto Docker Hub. Okay, I'll do that. Probably first we'll try and execute it so that it is creating a runtime instance and we are using it. Okay, so to push this onto our page, we need to log in and then we'll just use this command Docker push. And to run the Docker image, I'm basically using this command. So Docker run -p, you can see that command is also given here. Like this. Build is done, right? And in order to run this, we are going to use this port number and the Docker image. So what is the image name? MLR cars v1. This is the image name you can see. So when I run this, the Docker image is getting containerized now. Runtime instance is getting created, and we are exposing that to port number 5000 only. 5000 to 5000, I'm mapping the port numbers. Done? Okay, great. I have these warning messages. Hopefully it doesn't impact, but let's see. Yeah, I'll take this. This is on the local host. I'll open and I'll run this, and you get this image, right? So that's basically how you can run your application. I can also try and check. This is a different host name, 172 now, and hopefully it works on this as well. It's not running on this because internally the mapping is not done. Fine. So on local instance, it is running, right? So this is basically the application URL that we are using. All right. So we'll cancel this. We'll get another command. Docker images. These are the two images. Docker PS. It will talk about the container which is running. Right. So local host, port number 5000, and we are exposing it to 5000 port number. Right. So that's basically your Docker containers. So you can basically try and push this image onto your repository. So when I say Docker login, it is asking us to log into the Docker hub using our credentials. And this is the URL. So I'm just going to use my, I don't remember my password, but let me try. Error response, incorrect username password. That's the problem. Oh, okay. Let me do one thing. I'll try to connect it from here. I don't remember my username password. Unfortunately, yeah, this is my username, correct? I don't remember my password in that case. Okay, fine. Thanks to the desktop, I'm able to now log in. So if I say login now, it will not throw any error. Docker login. It will say you authenticated. Login in your terminal, access to your account. So we are login succeeded basically. Now I want to push the image that I have here, Docker images. I have this MLR cars V. This is in my local machine, right? I don't have this on my repository here, right? So I want to push my image here, right? So let us try and do that. So this is my repositories. I don't have anything. You can create a repository like this and right, try to use this repository. But I'm canceling it. I already have one repository. Let us use that repository itself. So I'll use this command. I'll push this. This is my repository. And the image name that I want to push. Image is this. That's all. Image does not exist. Oh, I have not logged in first to create the image. Okay, very good. And yeah, so it's now getting pushed into a new repository altogether. Request access is denied. Upgrade. You understood the problem, friends, here? The Docker image I created was created without logging into the repository. I did not log into the account, right? So this is an image which has nothing to do with the repository that I have created on my Docker Hub. My repository is this, right? 360DigiTMG. This is my repository. So what I'll have to do is I'll have to first create the Docker image using that repository first. So for that, let me just recreate the command. I'll just run this once again so that I have the repository name mapped. Right, so I'll just run this, but this will not work out because I'm not in that location. I will go to that location and I'm just recreating the image once again. That's all. See, this is my repository. Okay. Here, the repository is this. Image ID is this. So image ID is same, as you can see, but this time I have the repository name mapped to the repository name that I have in my Docker Hub. Right? That mapping needs to be done. Now I'm pushing this image onto my online repository. So Docker push this image that I have. Now you're able to see that the image is getting pushed into that particular repository. So here in image, you will be able to see this repository once it is getting uploaded. So 615 MB content is getting pushed from my local machine onto the Docker Hub. Let it finish, we'll be able to see that. Now, if I don't push it onto my Docker Hub, the image is not accessible from different locations because the image is only sitting in my local computer. I can create as many containers as possible using my local image only in my local computer. But now, because I have pushed this image onto the Docker Hub, I can connect to Docker Hub from any different computer, and I will be able to implement the image and create a container on that different systems as well. So for example, I will give you the access. I'll make the image that I'm putting in Docker Hub. I'm going to give you the access to that particular image, for example, right? I'm giving you the access, or I'm making it public. So you will be able to log into your Docker account. And because you will be able to access this public image, you will be able to run the same container run image function that I am doing. And the image will be implemented in your machine as well. So the image that I created is used by you, and you will be able to run the machine learning model on your machine. Right? So that's basically how the Docker Hub actually helps in creating the applications. So this is pushed. The entire application is pushed. Now let us look into this image. I don't have the image. Yep, look at that. This is the image that I have created just now. Right? Few seconds ago, I have created this latest image, and it runs on the Linux operating system. The compressed file is 250 MB. That's basically shown here. You can see that, right? 2205 is the size. Okay, this is the entire content that we have pushed. These are the image layers. Okay, so you'll have bash, that is your OS level thing. Python version is 3.8.16. That's what we have set up. And by default, pip version is also installed. And using pip3, we are trying to set up everything here after copying the file. And then we are again copying everything after setting up the environment. 209 MB is what is getting installed. And then once this is done, we are executing the function. Right? Now, if you see here, I already have a container set up, right? So you can also access this and create your front end like this, right? So this is the image. Using this image, you can try and install it, and then you can try and run the machine learning model. This is how the Docker image and Docker containers are useful. I'll just delete the Linux images that we have used in previous cases. I'm just deleting this, not required. I'm also deleting this. I'm only keeping one image. This is in use. I'll just delete this. Looks like this is hand. So you can see Docker images. I'll have only one image now because the other things are deleted from the front end. And if you say Docker, yes, this is one container which is up and running. All right, this is in my local machine. The same image is being pushed onto the Docker Hub as well. So in our next class, that is tomorrow, I will be showing how we will be using this Docker image, which is pushed into the Docker Hub, right? And I will try and use GCP instance altogether. So you can see this is specifically designed for that. So on GCP instance, I will be using Kubernetes engine, that service, register or basically create a cluster, use Docker account, log into Docker, my Docker account on the GCP, and then try to access this particular image and deploy this application on GCP service, on Kubernetes engine, right? So we'll try to do that in tomorrow's class. Yeah, any questions today in this part?
Yeah, sure. As far as I understood, basically Kubernetes is just like an orchestration tool like MLflow and
Yes,
Airflow.
that's right. Absolutely. And it is also having the special tag. I mean, it is created so that we can maintain multiple containers if required, right? Auto scaling is one of the primary features that Kubernetes engine has.
Okay.
Yeah. Any other
Uh,
questions?
Sharath, I have a generic question. So we discussed deploying a model on SageMaker, right? So
Yes.
is there any other way in AWS where we can still deploy models without using those kind of end-to-end platforms like SageMaker?
Did I not cover the setup of locally? I mean, we also did that, right? We have not used SageMaker completely. We used Notebook, and whatever the trained model that we have in our local machine, we use that trained model on XGBoost is what something we have done, right? Remember, on Notebook instance we used, and then we deployed the Notebook instance. Sorry, machine learning model using that. We have not used end-to-end SageMaker autopilot.
Okay.
So there are basically two things that we use. Where is my Epic pen? Let me open that. Sorry. just use this. So when we started, we used autopilot, which is an auto ML feature in AWS. And this service is basically called as SageMaker service, which is specifically used for machine learning model development, maintenance, building, right? All those things. So autopilot is one service, but we also used notebook instances. Notebook instance is basically a Python environment, a virtual machine, which is created only for Jupyter Notebook environment. So we created an instance. We took this Jupyter Notebook instance, loaded a locally trained model, right? When I say locally trained model, we have also used the code or the saved model, the image saved.
When you say notebook, this is Jupyter Notebook, right?
Yeah, it was giving us Jupyter Notebook page, right?
And that we have taken from SageMaker itself, right?
SageMaker is just a service.
Okay.
Under which we have taken only Python instance, I mean Jupyter instance. That's all. We have not taken autopilot service.
Okay.
So it's like we are taking one virtual machine. Under that virtual machine, we have Python installed and Jupyter installed. So we are only taking this. And this is basically available under SageMaker. Because SageMaker is like a service which allows you to use multiple resources which are interconnected. So we can call required services directly from this Python environment for deployment. Ultimately, you need machines, right? So that can be done using the SageMaker as a complete service. See, if you are saying, no, I don't want to use SageMaker service completely, then we can do the same thing by using only virtual machines. So you'll have to bring in a standalone virtual machine. Then
which is like
in this standalone machine, sorry?
Is it on the EC2 instance?
Yes, when I say VM, it is EC2 instance. This is also EC2 instance only.
Okay.
But in this EC2 instance, the software is readily available to you. Because we are only interested in Python software here, right? So that's the reason why we get only Python Jupyter Notebook instances readily available in the EC2 instance. None of the other services are used here. So billing will be only for that perspective. So if you use EC2 instance, standalone EC2 instance for creating a virtual machine, then you will have to install Python. You will have to install all the dependencies. And then you will have to probably load or copy paste the data and the code onto that EC2 instance, then execute your entire. So this is a manual effort. But again, if you want to deploy it, you'll have to probably take a different EC2 instance, put the saved model, the Flask code, all those things have to be moved here. And then you have to ensure that the service is up and running always. This EC2 is exposed to the external environment. Right? So this is basically like whatever you do on your local machine, you're doing on EC2 instances. So the network handling, these dependencies handling, and all those things will be external work for you, additional work for you, which is automatically taken care of if you use SageMaker. Here also you're doing manually only. But with respect to the maintenance, dependencies, and all those things, a lot of work is readily available for us. Autopilot is like completely automated. Everything is automated. Okay, so these are the three different scenarios. This is something you will not be able to do it very easily. You need to have a lot of network related knowledge. Right? You have to be very thorough with your entire ML services, I mean, your cloud services and all that. This is for data scientists. This is for probably more matured and cloud practitioners. Software developers, you can say. we can use the cloud services.
Okay.
Right. Any other questions with respect to Kubernetes or anything that we discussed till now? Okay. So what about tomorrow? I just wanted to ensure that we have some understanding on what exactly has to happen tomorrow. Yeah, any more further questions with respect to the subject that we discussed till now? Okay, I'll ask you more questions. So let me stop the recording.